Hey guys, BuildZoid here, and today we're going to be taking a look at the ASUS ROG MAXIMUS Z790 Apex motherboard. The board was provided by ASUS, so big thank you to them for sending it over for testing. Before we get into this, a quick disclaimer. This is not a review, and I am not an engineer. I'm just a guy who finds motherboard power delivery very interesting. So, anyway, with that out of the way, let's get into it. I would consider the MAXIMUS Z790 Apex to be one of the most overbuilt motherboards ASUS has ever produced, and the best example of that is the capacitor selection for, like, well, everything. Because for some reason, with this board, ASUS decided that they just, or whoever designed this board basically decided that they hate through-hole capacitors. And so the only through-hole capacitors that you can find on this entire board are these ones in the audio section. But I don't care about the audio section, so these functionally don't exist as far as I'm concerned. So, yeah. And then on the rest of the board, we just don't have through-hole capacitors. And this is a very, I'd say, silly decision, because SMD polymers, both the tantalum variety and the aluminum polymer variety, are very, very, very expensive per microfarad compared to their through-hole counterparts. And the end result here is that, like, well, like, the PCIe slot filtering situation is just it's just ridiculous, because normal practice for a lot of motherboards is that you would have a 16 volt 270 microfarad capacitor, right, through-hole polymer capacitor, for filtering the 12 volts going into the PCIe slot, and then you'd have a 6.3 volt 560 microfarad through-hole polymer for filtering the 3.3 volts going into the PCIe slot. Now, because ASUS decided on this motherboard that they're just not going to use through-hole capacitors, they ended up in this wacky situation where instead of having, 2 through-hole capacitors handling the entire PCIe slot, we have 5. What I suspect are Panasonic SP caps, and the reason we have 5 of them is because these things are 16 volts, 56 microfarads. Yeah, they don't make aluminum polymers in high voltage ratings with high capacitance. That's just not a thing. So, in order to achieve that typical 270 microfarads per PCIe slot, you need 5 of these, right? Because that gives you about 200. That gives you 280 microfarads. So, like, already we have 5. Like, instead of 1 capacitor, we have 5 of them. These are also more expensive per microfarad, so this is just way more costly. This is just a way more costly way of filtering the 12 volt power for the PCIe slot than just using a 270 microfarad through-hole polymer. And at this point, you might be wondering, okay, but is there at least some kind of benefit to doing this? Well, I'd say no. And the reason I'd say no is because the main advantage of SMD polymers, like what we have here, is that they have significantly lower equivalent series inductance. The equivalent series resistance is often actually very similar, or sometimes even worse than their through-hole counterparts, though that's not really a concern when you put 5 of them in parallel, because the equivalent series resistance gets divided by the number of capacitors that you have in parallel. So even if these were, like, say, 15 milliohms of ESR each, that would end up being effectively a 3 milliohm ESR capacitor bank, right? Which is still low. Like, typically you can get 16 volt through-hole capacitors at like 7 milliohms or 5 milliohms of ESR for, like, the through-hole capacitors. So that's not really, like, from an ESR perspective, this is probably about the same as if they just used a 270 microfarad through-hole polymer. But from an ESL perspective, this should be significantly lower ESL, which, would mean, which is an actual advantage for power filtering applications where you have fast transients. Having less equivalent series inductance is a good thing. The thing is, this is for filtering a PCIe slot's 12 volt power, like 12 volt power. GPUs typically have an input filtering inductor, which has many orders of magnitude more inductance than these capacitors. So basically, the main advantage of these capacitors is that they have a very low equivalent series inductance, right? So we can just sort of simplify that down to these have low inductance. These are like low inductance capacitors. And then we connect them in series with an inductor, thus completely negating the low inductance benefit of these capacitors. So, yeah, this is pointless as far as I'm concerned. There is no benefit to have like filtering your PCIe slot with 5 SP caps instead of a single, like FP cap or something from Nichicon. Um, there's no benefit to this, as far as I'm concerned. And what's even funnier is if you consider something like an RTX 4090, the RTX 4090 doesn't even like use the 12-volt power supply from the PCIe slot for anything important. Like all of the vCore power and all of the memory power on a 4090 comes from the 12-volt high power connector. It doesn't come from the motherboard. Something like an RX 480, the AMD old mid-range GPU, the RX 480, yeah, that pulls a significant amount of power from the motherboard. An RTX 4090 doesn't. An RTX 4080 doesn't. An RTX 4070 Ti, I'm pretty sure, doesn't. So yeah, this, and even on the RX 480, you do still have an input filtering inductor. And off the top of my head, I want to say it's like 470 nanohenries, which is, well, way more than these capacitors. So, yeah, this is very silly and utterly pointless from like a actual, like, does this do anything for your GPU's overclocking capability? No. Not at all. Like, it just doesn't matter. And then we get these tantalums on the 3.3 volt rail, which is the same situation. A lot of GPUs will have an input filtering inductor on their 3.3 volts as well. And then you have to consider the fact that 3.3 volts is usually used for just like powering VRM controllers and stuff. And it's like, yeah, because that's going to really produce some serious transients that, are going to really benefit from having low equivalent series inductance capacitors behind the PCIe slot. So, yeah, this is totally unnecessary. And because ASUS decided that they just hate all through-hole capacitors, this sort of design situation is just everywhere on this motherboard. Like, what do you think the 5 volts for your USB ports is filtered with? Yeah, more tantalums. There are motherboards out there that don't even bother filtering the USB ports at all. And then there's the Z790 Apex where it's like, yeah, tantalum polymers for filtering the USB ports. Because that's gonna achieve anything. And, then you have like, we have these tantalums over here, which I'm not even sure what these are for. They might be for like chipset power, which is like, who actually cares about the chipset power delivery? Then we have more tantalums over here. Like, and these are like expensive capacitors, like, especially compared to their through-hole counterparts. These are really expensive per microfarad, like easily 10 times the cost. And yeah, ASUS just they decided they're not going to use through-hole polymers, so they have to use these expensive capacitors absolutely freaking everywhere, right? We have more of them by the 24 pin. We have them used for input filtering for the memory power delivery. Actually, this isn't even memory power delivery. This is the VDD2 rail, which is just power for the memory controller. Like, also, I think these might be for filtering the power going to the, like, DIM.2 slot thing. Like, and then you go to the back of the board, and then it's like, oh, usually on a motherboard, you'd have, like, a 270 microfarad capacitor for filtering the 12 volts coming in from the 24 pin. Yeah, well, we can't do that because we're not using any through holes. 5 more 56 microfarad SP caps. So yeah, this is very excessive. And now there's one place you might say, okay, so, like filtering your 24 pin with SP caps and filtering your PCIe slots and USB ports with SP caps and tantalum polymers is obviously, like, this is unnecessary. But, you know, like, filtering the, say, the V-core power delivery, that might actually have some benefit. And, yeah, I don't think so. The thing is, like, and admittedly, like, I don't have oscilloscope measurements to sort of back this up, but based on my experience measuring various power, like various VRMs on GPUs and motherboards, the input filtering capacitor configuration kind of doesn't matter that much, just in general. And so this right here, I would like, you know, I think this is somewhat less silly than this. But overall, I still don't think it actually serves any functional purpose. And that's probably the reason why, with the Apex Encore, right, which is like the new version of the Apex from ASUS, ASUS decided to start using through-hole polymers again. Because they came to the same conclusion that I'm sort of presenting here, where it's like, yeah, this is dumb, this is unnecessary, this probably doesn't actually achieve anything. And so with the Apex Encore, like all of these capacitors that I've highlighted, or like most of them, because I think they're still using some SP caps in this area because of like there's that M.2 slot and they need to fit you need to fit the capacitors under the M.2 slot. In that scenario, your through-hole polymers kind of have the problem of they're very tall. Yeah, for all of this and basically all of this gets replaced with through-hole polymers. The filtering for the PCI slots gets replaced with through-hole polymers, and it's just like, yeah, because that's the reasonable thing to do. And honestly, like, I would not be surprised. So, fun fact, the Apex Encore is actually $50 cheaper by MSRP than the white Apex that we're looking at here. I would not be surprised if a significant part of that price reduction is entirely due to the switch away from like SMD polymers being used for absolutely everything. Because these things are really expensive as far as capacitors go. Like, yeah. The Apex Encore, like, I would really not be surprised if a good chunk of that price reduction is just because they decided to use more, like, sensible capacitor choices. Technically, more cost-effective capacitor choices, but, like, it's not corner cutting because it doesn't actually make a difference. And funnily enough, in terms of, like, endurance ratings, through-hole polymers actually have higher endurance ratings than SMD polymers. Not that I think it actually matters. I've not really encountered any scenarios where like SMD polymers have actually failed that were like, if you like overvolt them or like overheat them intentionally. And when I say overheat them, like heat them like a lot, like well over 120 degrees or something for extended periods of time. Yeah, then they do degrade. So like I've not actually seen a scenario, like I've not run into a scenario where like the endurance rating of polymer capacitors actually really matters. Because polymer capacitors just inherently are very robust and they don't really have a catastrophic failure mode unless you misuse them, as in overvolt them or overheat them, like massively overheat them. So, yeah. This board is very overbuilt, and the capacitors are sort of the best example of that, in my opinion. Anyway, let's sort of go back to where I usually start my PCB breakdowns, which is with the rear I/O, which I would consider to be sort of peak rear I/O. Or yeah, like this is like my idealized rear I/O, right? Because you've got your clear CMOS, your BIOS flashback functionality, got your PS2 ports for the mouse and keyboard. These are on there because in certain extreme overclocking scenarios, your regular USB ports can end up not working. These tend to still work even when everything else on the motherboard is starting to like have stability problems. So that's the reason why you'll see PS2 ports included on a lot of like extreme overclocking focused motherboards. And we get a whole bunch of USB Type A, which is basically the only type of USB port I care about. There's also 2.5 gig LAN, which is, for some reason, my notes don't say what 2.5 gig LAN manufacturer this is, but I also don't care. There's this Type-C port. We have Wi-Fi 6E, which I'm going to guess is from Intel, and then a full set of audio ports. So, yeah, if every motherboard had rear I/O like this, I would never have to worry about the rear I/O again. Like, I would just not bother checking it. Anyway, then internally, there's a bunch of M.2 slots that I don't care about, so we're just going to ignore them. What I do care about, though, is that this board does have X8 support, so there are PCIe switches on the back of the board. These guys over here, these are Gen 5, and so what that means is you can actually do X8, well, so you have the option of like X16, X8, or with like X0 or X8, right? Because the way this works is you have 8 lanes that permanently go to this PCIe slot, and then the other 8 lanes go into the PCIe switches, which are sort of down in this area. And then those 8 lanes either get sent back up or sent down to this PCIe slot. So you can have like the board has SLI support, basically. It also has Crossfire support, but like Crossfire is fun in that it'll work on literally any motherboard as long as you have at least 2 X4 PCIe slots. Like Crossfire doesn't have any real hardware restrictions. So, or well, real like software restrictions. Because with NVIDIA, the issue is that there's like an SLI license that you need. Actually, I'm not sure if this has an SLI license. So this might not have an SLI license. I'm not 100% certain. But it does have dual X8 support, which I'm a big fan of because you can convert PCIe lines into absolutely everything. The same is not true for M.2 slots. Anyway, let's move on to the overclocking features. We do have a postcode here. It's unfortunately not the giant postcode that they put on the Z690 Apex. I really like that. Like it was just absolutely huge. It was like this big. And, you know, it's a little thing, but I do appreciate, like, I do kind of appreciate the giant postcode, because then you can, like, tell if why the motherboard isn't posting from, like, across the entire room, instead of, like, standing right next to it. But anyway, we do still have a postcode, which, you know, is kind of the bare minimum requirement for an overclocking motherboard, in my opinion. You can't really consider yourself an overclocking board without a postcode, especially on the Intel side. We do also have some LEDs above that that are like color-coded boot-up sequence LEDs. But they're kind of made redundant by the postcode. Then we have the safe boot button, power button, reset button, and I really appreciate the fact that the safe boot button isn't right next to the retry. Like that they actually split them apart. Because there's a bunch of motherboards where you'd have like power button, reset button, safe boot, and then retry. Right, and then the obvious issue with that is like, yeah, so you have like the hard reset button and the safe boot button right next to each other, and it's just kind of like basically what I've done on a lot of motherboards is I've actually like Sharpied one of the buttons a different color just so that it's easier to tell which one's which. So I do appreciate the fact that like they've just put them on completely like really far apart from each other. So that's cool. Also, the safe boot button, basically what it does is it boots the motherboard with like auto settings, and it doesn't wipe your BIOS settings. So if you punch in something stupid and it doesn't want to post, you press the safe boot button, all your stupid settings are still there, and you can go fix them without them getting like deleted. So this is basically one of my favorite buttons to ever be put on a motherboard. Anyway, below that we have the power button, reset button, well, flex key, which by default is a reset button, but you can actually change the functionality of that button to a few different options in the BIOS that I don't remember what they are. Retry button, which is a very hard reset. This basically is the equivalent of turning off the power supply to restart the system. So this always works, because you can sometimes crash the CPU so hard that like your reset button stops working and your power button stops responding. Safe boot will still work, but you might not want a safe boot, right? You want to just reset the system. And in that scenario, the retry button is very convenient. Like, obviously, you could also just hold the power button for 10 seconds. That kind of does the same thing. but this is faster, right? You can also use this to force memory retraining, which I don't think the holding for power for 10 seconds will actually do that. Anyway, below that we have BCLK up and down. Really convenient if you're doing like frequency validations, so you can just sit in the OS, right, raise the BCLK, take your screenshot, raise the BCLK, take your screenshot, raise the BCLK, take a screenshot, kind of thing. And then below that we have the LN2 mode jumper, which just enables some of the, I think it mainly enables these switches as well as potentially preload some voltages for extreme overclocking. And in terms of what we have here for switches, we have a pause switch, which basically freezes the system. This is really convenient if you want to like pause on a loading screen in something like 3D Mark, change some settings, and then resume. Then there's slow mode, which sets the CPU to the lowest possible speed. And then below that we have the reserved switch, which I don't actually know what it does because what the reserved switch does on ASUS motherboards changes based on like what motherboard it is and what BIOS version you're on. Historically, this switch has preloaded LN2 voltages, so like voltages to get rid of cold bugs and stuff. But yeah, I'm not sure what it does here. Anyway, next to all of this, we also have a bunch of voltage read points, and these are actual through holes, not just solder bumps, which I really, really appreciate because, yeah, there's a lot of motherboards which will implement voltage read points where the voltage read points are literally just like little bumps of solder on the top layer of the board. And the issue I have with those is if you try to like, if you're trying to probe those voltage read points, the probes have a tendency to, and your probes aren't very sharp, the probes have a tendency to slide off of the solder bumps, which is really annoying. So by having them be through holes, the probes, even if your probes aren't super like sharp, your probes aren't going to be sliding around anywhere because these are holes, right? Like the probe is going to stick into the hole and it's going to stay there. So you don't have to pay a bunch of you don't really have to pay a lot of attention to how your probes are hooked up. Potentially also it would be easier to like put hooks through these if you want to like permanently get the probe. Like, yeah, if you have like some kind of hooky type probe, you can actually hook onto these much more easily and then the probe won't go anywhere. So yeah, I really, really this is the best way to implement voltage read points, as far as I'm concerned. Like solder bumps are nice. This is nicer. So anyway, so we've got the voltage read points up there. Then down here we have a dual BIOS switch, and here are our two BIOS chips. And then we have some more switches over here. One of them is another reserved switch, and the other one is, I think, VLATch. But I don't actually know what either of those does. So, yeah. Anyway, is that everything in terms of features? Oh, there's also these white fan headers, which I love. I'm a huge fan of these because these are permanently locked at 100%. Or, like, they're not even, like, they just have 12 volts. Like, they don't have fan speed control. And I'm a big fan of them because if you're setting up a test bench, a lot of the time you just want airflow. And you want a lot of it. And you don't want to have to go into the BIOS to max out all of the fan speeds every time you clear the CMOS. You know, it's a little thing, but I just, like, I do appreciate these kinds of, like, little convenience extras that ASUS puts onto their Apex boards. Though I think my favorite implementation was actually the Z490 Apex, where you actually have a switch on that board that, like, hard locks all of the fans at 100%. I wish that functionality would make a comeback. So anyway, I think that covers all of the different overclocking features that we have on the board. So now, let's get onto the power delivery. And this is an awkward VRM to highlight because ASUS has wrapped it all the way around the CPU socket. And it's in, like, not one continuous piece because this part right here, and also, like, this over here is, like, another separate voltage regulator. So really, I should have highlighted it something like this. And I think this is 1.05 volts. I can't remember right now. It's like some minor voltage rail that doesn't really matter. Um, but anyway, this over here, that is, okay, I'm going to put it over here. This is VCC in, is what this section is. Then all of this is V-core. And then we have more V-core down here. Right? Anyway, so ASUS has wrapped the V-core VRM fully around the CPU socket. The idea behind this is that effectively you end, like, this is similar to how like GPUs now have like the V-core VRM on both sides of the GPU core. The idea is that basically if you're pushing current, like, yeah, if you're feeding current into the CPU from, you know, all sides, and it is worth noting that the actual pinout of the socket is something like this for V-core. I think it might also have like some inner pins. So like something like it might. I'm not sure. I haven't checked the LGA 1700 pinout, but like the CPU socket typically assumes that all of your power is going to sort of come in just from like this area, and what you can end up with on like certain motherboards is that you actually get like a lot of voltage drop from like say here to here. You'll have say like 100 millivolts of difference in voltage because all of the current is like trying to squeeze through this relatively narrow power plane. And so obviously that's like a bunch of power that you're losing because 100 millivolts if you're pushing like 200 amps is what, like 20 watts? Something like that, right? So that's just heat that goes straight into the motherboard. That's not ideal. But the other thing is like it can potentially have some negative like side effects for your voltage regulation. And so by basically feeding the power into the CPU from all directions, right? So like your power plane might end up looking something like this, which I don't actually know what like the internal layers of this board look like, so I don't know. For all I know, like it could be doing, like this board could be doing something very silly like the power plane does that, and then all of the current from like this phase has to go all the way around like this, and that just would completely defeat the purpose of putting these phases down here. But I'm gonna give ASUS the benefit that like I'm gonna assume that they're not doing that. Because yeah, this isn't like an NVIDIA GPU where a lot of the board design is like set in stone in terms of what you're allowed to do. This is a motherboard. And as far as I know, Intel doesn't really have a ton of restrictions on how board vendors lay out their power planes. So yeah, I'm going to assume that there's an actual like direct connection to the V-core pins in the socket from here to there. It doesn't have to do like some silly U-turn like that. And so, yeah, the idea is basically more efficient power delivery to the socket by just having a much wider power plane, effectively. So, yeah, that's like one potential benefit of laying out the VRM like this. The other benefit is you can squeeze a lot more phases onto the board. Or, well, a lot more power stages, because this is actually not a very super, like, this is not a super high phase count VRM. The controller over here is a Renesas RAA 229131, which can go up to, I think, 20 phases off the top of my head, but here it's running as just a 12 phase. And the reason it's running as just a 12 phase is because ASUS wanted to use 24 power stages, so we actually have, like, 2 power stages in each phase. So like this will be like one phase, and then you'll have another phase will be like another 2 power stages. And the way this is set up is they basically take one PWM signal and they just shove it into 2 power stages at the same time. So those power stages are in phase with each other. They switch on and off at the same time. And there's no real like downside to doing this. Like it doubles your current handling capacity per phase. Which is why this is like super popular on motherboards these days, because yeah, it's a very like cheap and simple way of really increasing the current handling capacity of a VRM without like significantly increasing the complexity of the board. So yeah, that's what ASUS is doing here in terms of the like control scheme for this VRM is just like, yeah, it's a 12 phase with 24 power stages. As for the actual power stages being used, we're looking at a bunch of Renesas RAA 2201054s. These are 105 amp smart power stages from Renesas. They are very efficient, and yeah, they can handle, like, you wouldn't actually want to run 105 amps through them because the heat output, like the combined heat output of the VRM at that point would be just through the roof. Probably in the range of like 200 watts or more. Actually, easily more. Easily more than 200 watts combined for the entire VRM if you were doing 100 amps per power stage. But yeah, like this is more of like a performance class than it is an actual like practical design number. Right? Like if you have 105 amp smart power stages, like, yeah, technically under very specific operating circumstances, you could run 105 amps through this power stage. Realistically, you should never do that because it'll be uncoolable. But that's why we have 24 of them. Because for a 14th gen CPU, like a 14, like, well, for the CPUs that you can put into an LGA 1700 socket, you know, you might be pushing something north of like 200 amps and pushing 200 amps into the CPU. And this is like, even at stock, actually, this is like, this is very low current for most, like for the high core count CPUs that can go into this socket. Even at stock, they'll pull over 200 amps, depending on what like software you're running. But you know, if you're not loading something, like if you're not loading the CPUs that hard, or you have one of the i5s, 200 amps output current, you'd be looking at only about 16 watts of heat being produced by the power stages in this VRM. That's not accounting for heat, like the heat produced in the inductors or the power plane, right? Like there's more power losses than just the power stages. But in the power stages, it would be only about 16 watts of heat. And spread across 24 power stages means, yeah, you could run 200 amps into the CPU without even having a VRM heatsink, because at this kind of like, at less than 1 watt per power stage, the like PCB of the board and the power stage itself will be perfectly capable of dissipating all of that heat on their own. Right. Also, this board uses an 8-layer, as far as I know, this board uses an 8-layer PCB. And that is relevant because on like a 6-layer PCB, you do actually, like how many layers the board has does affect the like heat dissipation capabilities of the board itself, as well as how much heat is produced by the power plane, right? Which can become like a real concern if you have like there are certain motherboards out there where you'll have like really high-end power stages on something like a 4-layer PCB or a 6-layer PCB. And it's like, yeah, the power stages aren't really producing a lot of heat, but the power plane is, right? Which obviously isn't a concern here because we have this like U-shaped VRM with an 8-layer PCB. So, yeah, but that is worth considering, that there are other like power losses in the power delivery than just the power stages themselves. Anyway, 300 amps output current, the VRM will produce only about 22 watts of heat, which, yeah, like, again, you still don't need a VRM heatsink. 400 amps output current. Now the heatsink might actually become somewhat useful, as you know, the VRM would be producing about 30 watts of heat, and you'd probably also start seeing like significant amounts of heat being produced in the board itself. But yeah, this is still extremely good, right, in terms of like heat dissipation, and also because the VRM is laid out like in this U shape, like there is more space between the power stages, because there are motherboards out there that manage to pack 24 power stages in like, well, basically just this L shape, right? And so ASUS also gets like this like reduced thermal density benefit by laying out the VRM the way they did. And so even at 400 amps, like, you probably would need the VRM heatsink. I'm not entirely certain that you actually would. Yeah. Also, it's worth noting that 400 amps is really hard to cool. Like, I'm not entirely certain that you can even hit this kind of current draw on an LGA 1700 CPU with a custom loop. So, yeah, this isn't actually like this isn't a very realistic operating scenario. Unless you're on something like liquid nitrogen, in which case the VRM won't need a heatsink because on LN2 people don't run multi-hour stress tests, right? Um, you usually run benchmarks that are like a few seconds to maybe a few minutes, and it takes a while for a VRM this big to get really hot. There's a lot of thermal mass that you need to heat up, right? So yeah. Anyway, at 500 amps, which this is well into LN2 overclocking territory, the power stages would produce roughly 43 watts of heat, and at 600 amps, it would produce about, say, 53 watts of heat. Um, so at this point, like the VRM heatsink would definitely be required, but that would be if you were like running 600 amps sustained, which you won't, because this is like LN2 overclocking territory. So, yeah, it's an extremely overkill vCore VRM. Honestly, if ASUS decided to release like a downcosted version of the Apex, like an Apex Lite or something, and they like removed half the power stages, it would probably still be fine. Especially if they actually just removed half the power stages by like leaving out every other power stage. Because again, you would have that like reduced thermal density benefit of like there's a lot of space around each power stage, right? So the heat density of the VRM would be very, very low, even if the current handling capacity would be like half as much as what it is in this configuration. Actually, it wouldn't be half as much because again, due to that like thermal density reduction, you wouldn't get a linear like, you remove half the power stages, therefore the VRM only handles half as much current. You'd get slightly more than half the current handling capacity because of that reduced thermal density benefit. Um, so yeah, like that's how excessive this VRM is in this configuration. Is like, yeah, you could probably remove half of it and it still wouldn't really have any problems. Um, Also, I forgot to mention that these output currents are assuming an output voltage of 1.2 volts and a switching frequency of 500 kilohertz. Um, or like these heat outputs are assuming 1.2 volts output voltage and 500 kilohertz switching frequency for the power stages. Anyway, so yeah, as is as is pretty typical of a high-end Z790 motherboard, the vCore VRM is massive overkill. Definitely wasn't expecting that. Anyway, let's talk about the filtering for the vCore VRM, which I am a huge fan of. I complained about the SP caps on the PCIe slots and the tantalums on the USB ports, but man, I am a huge, huge fan of 3-terminal SP caps, which is exactly what we have here. And what I mean by 3 terminals is you'll notice that there's like these pads right here. And so the way that's actually laid out is, wait, do I remember? Yeah, it's something like, yeah, so you have a pad like this, and then you have a pad over here, and then you have a pad over here, right? And this is the positive end, and these are the grounds. But anyway, so the 3-terminal version of the SP caps is basically like, so SP caps normally have the whole like low equivalent series inductance as an advantage over their through-hole counterparts. What if I told you you could have less equivalent series inductance by having more terminals? And that's what these are. So regular SP caps only have 2 pads, and these have the 3 pads, and the 3 pads basically allow an even lower equivalent series inductance, which means these are even better for filtering fast power transients, like what you would see on the vCore power rail of a high-end, high core count, like of a high core count modern CPU. So yeah, and for vCore filtering, we've got, this is 470, this is a 330. I'm not sure if this one belongs to vCore. Anyway, these are all vCore. These are all vCore. Oh, I guess I should have pointed out this motherboard doesn't have an iGPU power rail. Yeah. I mean, I personally don't care because I don't think I've ever used the iGPU on an Intel CPU, on like a desktop Intel CPU. Obviously laptops, yeah, but desktop Intel CPU, I don't think I've ever used the iGPU. Um, but anyway, so yeah, we have all of these 3-terminal SP caps for vCore. These ones, I mean, I'm not 100% certain that this one isn't vCore, but these two, these belong to the VCC in rail. Yeah, all the rest of these are for vCore, and in total there is 20 of them. So that's 9. Oh, okay, so this one's also vCore, because that way we have 5, 9. Wait. Oh, there's also one more on the back. Yeah, so this one's also vCore. But yeah, so 3-terminal SP caps. These are 470 microfarads each. So there is a lot of capacitance here. And if we actually go to the back of the board, there's one more in the CPU socket. Now, interestingly enough, the back of the socket is kind of empty in terms of multi-layer ceramic capacitors, but considering how many like 3-terminal SP caps are on the front side of this board, I don't think I'm guessing that ASUS came to the conclusion that fully populating the back of the socket just doesn't make a difference at this point. Especially since on the like front side of the socket, like they did fully populate the actual like socket cavity with multi-layer ceramics on the front. So yeah, the back of the socket is like kind of optional in this scenario. Also, I do kind of like I'm kind of a fan of seeing all of the like stitching for the SP caps into the power planes. Just kind of looks neat to see all of the little vias connecting them through the board. But anyway, so yeah, in terms of output filtering, like capacitor configuration, there isn't really a motherboard that I would consider better. Like this is as good as it gets. You have the like lowest ESL and ESR aluminum polymer capacitors that you can I'm aware of, and there's 20 of them. Like, yeah, it really doesn't get better than this in terms of vCore filtering on a Z790 motherboard. Also, we don't even have like insanely high inductance inductors by like ASUS motherboard standards. These are just 330 nanohenries. Not that the like inductance of the inductors matters that much. But like it's worth noting that if you have like very high inductance inductors, you do have the VRM will have a tendency to have more overshoot. Undershoot isn't actually affected because the issue with the inductant, like with undershoot, basically it's about how quickly the VRM can respond to the load insertion transients. But on load release, what basically sets how much voltage overshoot you have on load release is like how much energy is stored in the inductors, which is based on what inductance they have, and then how much energy storage capacity you have in your capacitance, and how quickly can that energy get stored in the capacitors. And well, there's a lot of capacitance here, and that capacitance is basically the fastest. Like the only way, like the only capacitors that have less ESR and ESL, actually not even ESR, just less ESL is like 0805 multi-layer ceramics. So yeah, and only having multi-layer ceramic capacitors for vCore filtering would get very, very expensive very, very fast, and probably wouldn't actually deliver. Well, you might not be able to get enough capacitance to justify doing that. Because you do like there is like a certain amount of capacitance that you need for the for the power delivery to work correctly. So anyway, yeah, so in terms of like vCore filtering, it doesn't get better than this. Like it just doesn't. So yeah. Anyway, for input filtering, I've already mentioned this. We have just an absolute ton of 56 microfarad SP caps. I didn't, however, mention how many they are. And it is a lot. Because it is 38. Yeah. Mostly because the capacitance is so low per capacitor. right? So yeah, there's 3856 microfarad SP caps for the input filter, which is just completely unnecessary, as I mentioned earlier in the video. SP caps on the output, good, and I approve. On the input, you could use something cheaper, as far as I'm concerned. So, anyway, let's talk about the VCC NVRM. So the VCC NVRM is pretty typical for a Z790 motherboard of basically any kind. I do believe this is the controller for it. Unfortunately, the label isn't legible, and it's been a while since I actually looked at the board in person. But anyway, that should be a Monolithic Power Systems MPS 2940 voltage controller, which is like, this is for some, like, this is like the standard VCCN controller of high-end Z790 and Z690 motherboards. Like, you see it absolutely everywhere. It's a two-phase. And for the power stages, ASUS is using 50 amp monolithic power systems MP 86992s, and yeah, these are 50 amp smart power stages. And VCCN just feeds the this just supplies 1.8 volts to the CPU for like VCCSA, and then the CPU down regulates that 1.8 volts into VCCSA, CPU VDDQ, and a bunch of other minor voltage rails. So this really, this is very overkill. A lot of cheaper Z790, a lot of cheap Z790 motherboards will actually just have a single phase single phase voltage regulator set up for this. And a lot of ITX boards, even expensive ITX boards, will just have a single phase VCC in because there's not physically enough space to have a two phase on an ITX. So yeah, this is massive overkill. And of course, the VCC in VRM also gets more 3-terminal SP caps for its filtering because why not? This board, we're filtering the PCIe slots with SP caps. We may as well filter VCC in with 3-terminal SP caps as well, right? Like, why? Is it unnecessary? Yes. Also, there is 4 of them, because of course there is. Yeah, these are also on VCC in. So, yeah, this board is just excessive in every way possible. Anyway, so that's VCCN covered. Oh, I guess the one thing that you can't say is excessive is the VDD2 voltage regulator. Because, well, to be fair, I think I've seen some motherboards with a simpler VDD2 regulator setup. But, yeah, this is the one place where I can't say, okay, these are, super fancy whatever components, because they aren't. I mean, I guess you could say 50 amp smart power stages aren't really that special, but these are still really good. But yeah, what we've got for the VDD2 rail over here is everybody's favorite cheapo MOSFET. Wait, is it? Yeah, it is. It's actually the On Semiconductor 4C10N MOSFET. There are motherboards that use this for their vCore VRM. I don't like those motherboards, but this is VDD2, and all VDD2 does is go to the, this is just a power rail for the CPU memory controller, that replaces, on DDR4 you had the VDDR rail, which is the DDR5, for DDR5 you have VDD2, with DDR4 you had VDDR. Same thing, except VDD2 has to power less stuff than the DDR4 version did, because the DDR4 version, it also powered the memory sticks. Now it just powers the memory controller. So yeah, using 4C10N MOSFETs here is completely fine. There's one for the high side, one for the low side. I've got absolutely no complaints for that. The controller is a ANPEC, wait, is it ANPEC? I'll just write the part number. It's an APW 8723A, single phase, single phase controller with integrated drivers. So basically it just means that it drives the MOSFETs directly instead of there being a separate driver IC. And yeah, for a VDD, this is a pretty standard, actually, like this is a pretty substantial VDD2 regulator, but yeah, these are very basic parts. And that's what you'd expect. Like this rail just doesn't have to supply that much current, so why would you use anything fancy for it? Though I say use anything fancy for it. Guess what capacitors are on it? Yeah, more 470 microfarad SP caps, the 3-terminal variant. And also, if we look at the back of the board, you have this lovely arrangement of multi-layer ceramics, because the VDD2 rail, like, is this, like, power plane. Like, it's used, it might be used, like, depending on the board, it might even get used as a reference plane for certain memory signals. So yeah, and that basically should do something like that, and then you have more VDD2 over here. So the filtering, like the MOSFETs used for the VDD2 rail, very basic. The filtering setup, kind of fancy. Because, yeah, like you've got those 470 microfarad SP caps, and then you've also got all of this ceramic hanging out in the memory section. So, yeah, like in terms of power delivery, when it comes to Z790 motherboards, it really doesn't get better than this. Like, it just doesn't, as far as I'm concerned. So, yeah. Anyway, the last thing to talk about is, I guess, the memory topology, which we're looking at a 1 DIMM per channel, so 1 DPC. So each, like, so the memory controller just connects to 1 DIMM slot. And then layer count, as far as I know, this is an 8-layer PCB. And we do actually have memory traces running on the top layer, which is kind of interesting because most other motherboard manufacturers, like say Gigabyte or MSI or ASRock, as far as I can tell, are really like doing their, like they're not running any of their traces on the top layer. Whereas ASUS, I think, runs the entire A channel, or at least all of the data lines for the A channel on the top layer of the PCB. And that's just like like design choices thing. In terms of actual memory overclocking capabilities, well, let's just put it this way. This is the only motherboard that I've actually had XMP run like XMP 8000 memory sticks run Y-Cruncher on without having to like bend over backwards. So yeah, though in terms of like max, well, I haven't actually tried to do a max memory clock. Like here's the issue. I really don't like memory overclocking on Intel CPUs. And unfortunately, the Apex doesn't change that because the Apex, I love the power delivery, I love the feature set. I really wish it didn't support Intel CPUs. Like if I could get this motherboard with an AM5 socket. But no. It takes Intel chips. And Intel chips have the Intel memory controller, and the Intel memory controller is incredibly cursed. And I do not enjoy dealing with the Intel memory controller. And like the Apex is a very good memory overclocker, but it doesn't fix the fact that the Intel memory controller is cursed. It just hits higher speeds. Like that's kind of the issue is like, yeah, if you have a weak Z790 motherboard, the Intel memory controller is cursed and that behavior like you run into that behavior at lower speeds. And if you have a good motherboard, you still like that behavior is still there. It just happens at higher speeds. So, yeah, that's like and in terms of like, is this a better memory overclocker than a Tachyon or a Dark? I can't tell you because the Intel memory controller, it like is so inconsistent that like on any given day, what settings will work on what board is basically random. And so like I just can't. Okay? Like I can't. I give up. I am no longer dealing with Intel memory overclocking. And the Apex hasn't changed that. Like, it is a very good memory overclocking board. Like, it'll run circles around 4 dimmers, but it can't fix Intel's memory controller. So, yeah. Great board though. And I think that's it for the video, right? We've gone over the silliness of the just general capacitor selection on this board. Like, seriously, like, like, the thing is, there are other motherboards that have done things like not use any through-hole polymer capacitors whatsoever, but those motherboards at least had the sense to use tantalums, right? Because you can get tantalums in like relatively high capacitances. So you don't end up in this situation where you need to put 5 SP caps next to the PCIe slot because each of these is 56 microfarads instead of something sensible like, I don't know, 150. But yeah, no, ASUS just kind of decided like they were just gonna make the most overbuilt motherboard that I think they've ever made. Um, And what? Because and by overbuilt I mean unnecessary expense. Okay, I don't mean like because the ASUS has all like ASUS has built motherboards with like more powerful power delivery. But even on those motherboards, because you know that would be like the Dominus Extreme for the W3175X Xeon. But even on that motherboard, they still went and used through-hole polymer capacitors in places where it made sense to use through-hole polymer capacitors. They didn't filter the PCIe slots with SP caps because that's just silly. But yeah, with the Z790 Apex, it's just like, yeah, through-hole capacitors are just not cool anymore, and so SP caps for PCIe slots. Yeah. Oh, also, actually, like one interesting thing of note about this board, there's no input filtering inductors on the 8-pin power connectors. Instead, we have these little shunt resistors. So I'm guessing there's some like some power monitoring functionality, but I haven't really gone through all of the ASUS software with this motherboard to figure out like if you can actually get a readout from these, or like where that readout shows up. But yeah, there does seem to be like current monitoring capability for like current going into the vCore VRM, which is kind of neat. Anyway, yeah, so that's the Z790 Apex. I'd say the most overbuilt motherboard ASUS has ever produced. I'm not necessarily saying it's the best. I'm not like the Apex Encore might actually be a better memory overclocker depending on if ASUS made some like further optimizations to the memory topology or something. But in terms of just sheer excessive like component cost, I don't think it gets like this. I think this is the most in that sense. So yeah. Anyway, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. Yeah, that's it. Wait, oh no, I also have a Bandcamp. There's a link to that down in the description below. And yeah, that's it for the video. So thank you for watching, and goodbye.